Hi everyone, this is going to be a review of LLRBs and 2-3 trees. If you guys want access to these slides, you guys can go to tinyurl.com/LLRB-slides. So let's dive in. I want to start with talking about what's the problem with binary search trees. So the problem is that they can become spindly, especially when numbers are inserted in sorted order. As a quick example, we can see after inserting the numbers 1, 2, 3, 4, we can see we have somewhat like a linked list where all of the elements are kind of going to the right. Okay, so this is a problem because in a BST or any tree for that matter, it's helpful if the tree is very bushy and balanced, right? So kind of a crazy idea here is, what if we think of some sort of tree where we don't need to add new leaves? So this idea is actually implemented or has a name, and it's called a BTree. So how it works is, instead of adding new leaves, what we're going to do is overstuff the current leaf nodes. So let's kind of walk through a quick example so we can gain intuition for what's happening. So looking at a 2-3 tree, after inserting the number 1 is we just have the node 1, okay? Then what we're going to do is insert the number 2. And what we're going to do here, which is different than a BST, is that instead of setting 2 as the right child of 1, right, this is what usually happens in a BST. Now what we're going to do is overstuff this 1 node by adding 2, okay? So let's add 3 and see what happens. So after adding 3, we see the state of our tree is an overstuffed node consisting of 1, 2, and 3. But a property of 2-3 trees is that the maximum number of elements that can occupy a given node is 2. Okay? So what we do in the case that we have 3 elements is we take this middle element, right? In this case, the number 2, and we push it to the layer above. In this case, there's nobody above 2, so 2 becomes the new root of the tree, and this is the final state of our tree. Okay? So let's walk through a couple more additions. So after inserting 4, we see that 3 and 4 are now part of the same node. Then we insert 5, and we see this node is overstuffed. So what we're going to do is take 4 and push her to the level above. So now this is the state of our 2-3 tree. Okay? So the next thing that we're going to do is let's insert 6 and 7. After inserting 6 and 7, we'll notice that this node is overstuffed. So what we're going to do is take 6 and push him to the layer above. Then what's going to happen is, this is our next state of the 2-3 tree, and we see that the root node is overstuffed. So what we're going to do is we're going to take 4 and push her to the layer above, and now in essence, we have a perfectly balanced tree, right? And one really, really cool thing is just looking at this 2-3 tree and then looking at the BST, and we can see that the 2-3 tree is perfectly balanced. So it seems a 2-3 tree is amazing, right? But the problem with 2-3 trees is that they're really hard to implement in practice, okay? But before we move on to a better solution, I kind of want to talk about two main takeaways for B trees, 2-3 trees more specifically. So when we have a node in a 2-3 tree, it can have at most 2 elements and at most 3 children, okay? And the second invariant is that all leaves are the same depth. And let's kind of walk through a quick example to understand why this is the case. Looking at the previous example, when we have the node 1, 1 is the root, 1 is the leaf, right? So now we see that just because there's only one person, the node 1 is the same depth from the top, right? So after adding 2 and 3, remember this was the state of our tree. Now that we actually have leaves, let's see here that 1 and 3 are the same distance from 2, okay? In the future, if we were to ever split the 2 node, split refers to that process of taking that middle element and pushing it to the layer above. What we'll notice is that if we have a new root, let's say we have some new root up here, since 1 and 3 were the same distance to the old root, and the new root is just 1 above 2, we know that 1 and 3 are going to be the same distance to the new root, right? And we can kind of generalize this logic for any pair of leaves. So let's move on to LLRBs, okay? The problem, just to recap once more, is that 2-3 trees are really hard to implement in practice. So what we're going to do, which is very clever, is we're going to say, let's take a 2-3 tree and let's change it into a form that's easier to implement, okay? That form is called a left-leaning red-black tree. So for every 2-3 tree, this is very important, there is one and exactly one corresponding LLRB. Looking at this example here, what we can see is that for this 2-3 tree, there is one and exactly one corresponding LLRB. So the next question you guys probably have is, how do we take a 2-3 tree and find the corresponding LLRB? Okay, so an LLRB is just a BST where some nodes are, or some links are red and some are black. Okay, the red links are the ones that are kind of new, and a red link represents two nodes that were overstuffed in the 2-3 tree. Okay, we can see here that the node 1-3 in the corresponding LLRB looks like so, right? Same for 8-9. So just to recap, what we're doing is we take this node 1-3 and we're going to set the bigger person, in this case 3, to be the parent of the smaller person, okay? And just to make life easier for ourselves, we're going to make sure that all the red links always go to the left, okay? What that means is that looking at this pair 1-3, we know in the corresponding LLRB, 3 will always be above 1, right? It will always appear in this orientation, okay? So let's kind of like walk through a couple practice examples to gain some intuition for what's really happening here, okay? So suppose we have this tree, okay? And we decide to add the number 0. What's going to happen is we're going to add a red link between 0 and 1. So why are we doing this? Well, recall that a LLRB has a corresponding 2-3 tree, okay? The only purpose of LLRBs is that they're easier to implement in practice. So every time we do something to a 2-3 tree, just imagine that there's an exact corresponding LLRB, right, that should perform the same way as with a 2-3 tree. What I mean by that is, recall this 2-3 tree that we mentioned before. After adding the number 0, we see that 0 and 1 are part of the same node. Likewise, when we think about the corresponding LLRB, after adding 0, 0 and 1 are part of the same node. Okay? So it seems that why don't we just always insert people, add red links, call it a day? But it's not always that easy. Sometimes when we insert, we're going to have a red link going to the right. This is a problem because an invariant of an LLRB, right, part of the name is that all of the red links go to the left, okay? Another property of an LLRB that we must preserve is that a node must have at least 2 elements, right? Recall that an LLRB is just an easier way of coding a 2-3 tree. What I mean by that is in a 2-3 tree, if we have the node 0, 1, in the LLRB, it's represented like so, okay? So in an LLRB, we can't represent a node, or we can't have the state when there's a node with 3 people, right? Because this isn't allowed in a 2-3 tree. So every time we perform an insertion in an LLRB, we have to make sure that these 2 properties hold, okay? In order to preserve these 2 properties, there's some ways that we can mutate the tree, okay? More precisely, there's 3 tricks that we can use. So the first trick that we can use is called a rotate left, and it works as follows. What we're going to do is we're going to take this node A, and we're going to rotate it to the left. More specifically, what's happening here is we're going to take A, kind of move it down to the left, and then we're going to take B, and B is going to fill A's void, okay? And this may seem kind of arbitrary, like why are we doing this? When would it be helpful? So I kind of want to walk through the problem that we face after adding 4. Notice here that this is a problem because 4 is on the right of 3. What ideally we want is we want 4 to occupy this node, and then we want 3 to be the left child of 4, right? This is what we want. In order to make this happen, what we can do is we can take 3, rotate it to the left, so that 4 fills 3's void, and then 3 becomes a left child of 4. So this is an instance when we want to perform a rotate left to take that red link, which is going to the right, and then point it to the left, okay? But after performing a rotate left, we usually have to deal with these subtrees, okay? The children of A and B. Like, how are we going to deal with them? So let's walk through a quick example before we actually look at this diagram, okay? Looking at a quick example, let's say that we have 2, 4, 3, and 5, and let's say we have 1 here, okay? This is just a regular BST. There's no red links. So if we decide to rotate 2 to the left, what's going to happen, this is how I like to do rotations in my, like visually, is if I'm rotating 2 to the left, let's say this is 2, this is 4, what we're going to do is it goes like that, okay? That's how I like to think about rotations, right? We're rotating 2 to the left. It's going to look like so, okay? So how that's going to look is, oh gosh, we're going to have 2 and 4 like so. Now what we need to do is figure out how to deal with 1, 3, and 5, okay? So for 1 and 5, we're going to keep them in the same place as before. What I mean is that we're going to keep 1 as the left child of 2. We're going to keep 5 as the right child of 4. The missing person here is, what are we going to do with 3? Okay, what are we going to do with this kiddo right here? So notice that all of the elements that fall in this subtree are in between 2 and 4, okay? So what we want to do is put this subtree in the same place, right? We want to put that subtree still between 2 and 4. So what we can do is we can set 3 as the right child of 2. Now what we can see is that this subtree is between 2 and 4 in this tree. In the new tree, it's still between 2 and 4, right? And if we want to see a quick, more generalization of this, that was not good wording, but looking at this example right here, we see that in general, when we want to perform a rotate left, looking at the subtrees X, Y, and Z, we're going to take A, right? And we're going to keep X on the left of A because X corresponds to all of the elements less than A. We're going to take Y and put it as the right child of A, right? Because Y corresponds to all of the elements between A and B. Then we're going to take Z and keep Z as the right child of B. So let's move on to rotate right, okay? How rotate right is going to work is symmetric to rotate left, except now, instead of taking the root node and rotating her to the left, we're going to take the root node and rotate her to the right, okay? Visually, how that kind of changes is that in a rotate left, it kind of goes like this. In a rotate right, it looks like that, right? Where this is my top node that we're rotating to the right. This is its child, and it looks like that, okay? So looking at this rotate right, let's kind of walk through it really, really quickly, just so we can see it's the exact same as rotate left, just in the opposite direction. We can see here that if we're rotating right on B, A is going to stay as the left child, or X is going to stay as the left child of A. Z is going to stay as the right child of B. The only difference is Y, right? It changes from the right child of A to the left child of B. Okay, so that's kind of how a rotate right works. So for a quick understanding check, let's walk through these two operations. Rotate right on 3 in this tree, and then rotate left of 1 on this tree. So I recommend pausing the video, trying this on your own, and then I'll walk through it in 2 seconds. Okay, so let's quickly walk through it. When we perform a rotate right, I like to do my hand action. I'm going to show you guys once more. We take 3, we rotate her to the right, like so. So how that's going to look is now 1 fills that void, right? And then what's going to happen is that 0 will stay as the left child of 1, and then 2 will become the new left child of 3, okay? And intuitively, 2 makes sense here because it's in between 1 and 3, right? So this is the proper place to put it. So looking at this other example, when we rotate left of 1, how that's going to look is that we take 1, we rotate 1 to the left. So we see here that 3 fills the void. And what's going to happen is that 0 stays as the left child of 1. We see that 2 is going to change from the left child of 3 to the right child of 1. Okay, so those are a couple quick checks. And then the last couple things I want to mention is when we have a 2-3 tree, right? Suppose that we have this 2-3 tree. This is the exact same 2-3 tree that's mentioned or corresponding to this LLRB, okay? If we have this 2-3 tree, what we want to do is we want to take this number 2 and push it to the level above. In doing so, our tree will look like so, right? That's what we want to have happen, okay? Since a 2-3 tree has a corresponding LLRB, how do we execute this operation in the LLRB, right? There must be some way to take a node in a LLRB and push that node to the level above, right? Because a 2-3 tree and an LLRB are essentially the same, right? So what we're going to do, actually I'm going to bring that back, is we're going to perform this thing called a color flip on the node that we want to push up to the upper level, okay? So looking at this node 2, we can see that in order to push it to the level above, this is really, really cool. All we have to do is flip the colors of all of the outgoing links at 2, okay? And what that really does is that it pushes 2, so now 2 and 4 are part of the same node, okay? So just to recap, in a 2-3 tree, we have this process called splitting, where we take an element, we push that element to the layer above. In a LLRB, we have to have some way of executing this operation. So our way of executing that operation is called color flipping. How a color flip works is that we take all of the outgoing links off a given node and we flip their color, okay? So the last couple things I want to say are, when do we actually use rotations in LLRBs, right? So we remember that if we ever have a node to the right, we perform a rotate left. But when would we ever use a rotate right? We want to perform a rotate right in this following situation, okay? More specifically, what we want to have happen here is we want to eventually perform a color flip on this component, right? Because in the corresponding 2-3 tree, we see that it looks like so. But in this current state, we can't perform a color flip because a color flip can only be performed in this configuration. So what we need to do is prepare to color flip by taking 3 and rotating him to the right, okay? So that's what we mean by preparing for a color flip, is that we take a node and then we rotate it so that in the future we can perform a color flip. So a final thing, last slide, I promise, are a few key takeaways is that when we have some sort of insertion into an LLRB, we need to apply a rotation or a color flip if one of these situations occurs, right? If we have a right leading red link or a node is overstepped, right? Finally, we can check our work in a couple ways. Looking at an LLRB, it should still be a BST, right? What I mean by that is all of the nodes that are smaller must be to the left, all of the nodes that are bigger must be to the right, okay? And then the last way of checking our work is that all leaves should be of the same height. Recall in a 2-3 tree, this is the case, and an LLRB is representing a 2-3 tree. So that is all for this walkthrough. Hopefully it was a good review, and good luck on the worksheet.